Olá a todos, meu nome é Hélio Dias, presidente do IVPESP, que é o Instituto para a Valorização da Educação e da Pesquisa no Estado de São Paulo. Somos uma entidade de direito privado, sem fins lucrativos, e nosso objetivo é se tornar uma ponte entre a sociedade e o conhecimento. Contamos com membros representativos da sociedade científica, empresarial e universitária. Contamos com um centro de inteligência e especialidades multi-institucional e multidisciplinar, com membros do Brasil e de outros países. Em nosso portal, vocês vão encontrar as nossas principais ações até o momento, que são workshops, encontros temáticos, feiras e informações de interesse da sociedade na área da divulgação científica. Nosso principal objetivo é tornar o conhecimento acessível a todos e contribuir para o aperfeiçoamento das instituições. O IVPESP conta com um certificado de regularidade cadastral de entidades do Estado de São Paulo, o que nos credencia para parcerias com entidades públicas e privadas. Você vai assistir agora a mais um evento organizado pelo IVPESP. Obrigado e boa palestra a todos.
I start with the usual apology that I have to give my talk in English because despite having been to Brazil for at least 10 times, I still do not manage to speak Portuguese. But I hope that I get the main message across in English too. So what I want to talk about is a new approach that we are thinking about at Michigan State University and that we have been planning for the last 3 years. I should probably say where Michigan State University is. So this is an unusual view of the world showing the northern hemisphere. And Ilya, do you have that pointer? And up there between the big lakes, that's the state of Michigan. And Michigan State University is located right in the middle of it. So this is a picture of our campus. All the buildings that you see here belong to the university. So the university is not distributed all over the city, but actually maybe twice as big as this picture. I took this picture out of an airplane, so couldn't really position myself. Michigan State University was established in 1855. It has a lot of land. 5,200 acres is about 2,000 hectares. There are a total of 577 buildings, 83 of which are used for lectures and instructional purposes. We have 36,000 undergraduate students up to the bachelor degree, and then 11,000 graduate students, master and PhD students. About half of our students are women. We have about 430,000 students that have graduated from the university, and we employ about 5,000 faculty and academic staff. We offer 200 different degrees in different subjects in 17 colleges, and we're consistently ranked one of the top 100 universities in the world by rankings like the Shanghai rating or the London Times higher education ranking. My own department is the Department of Physics and Astronomy. Until I stepped down last year as chairperson, I did this for 13 years, and up there this was my office. We have the #1 ranked nuclear physics program in the United States. About 5 years ago we passed MIT, which held this rank before us. Our annual personnel budget is about $8 million, and we receive about $30 million in federal grants, which will go up to about $60 million in 2 or 3 years when our new accelerator project is completed. So we just received a grant from the U.S. Department of Energy for $650 million construction of a new national lab on our campus. And we have 70 faculty members of all ranks. So what we have been doing in teaching is basically follow a standard curriculum that most universities in the US and around the world follow. So when you want to study physics or engineering, you have to take, well, basically these courses and the courses on the next page, but there's mathematics, and so it's a 3-semester sequence of calculus 1, 2, and 3, and you can read the topics. It's anything from one-dimensional differentiation and integration to multivariable calculus, to vector calculus, line and surface integrals, the typical things that you do in math. In physics, we have 3 introductory courses. The first one basically deals with Newtonian mechanics. The second one basically deals with electricity, magnetism, and optics. And then the third one, thermodynamics and what people call modern physics, which is not so modern anymore because all this modern physics was done about 100 years ago. Theory of relativity, quantum physics, atomic physics, but then also leading to most recent results in nuclear physics, condensed matter physics, and elementary particle physics. And then there are some lab courses that go with these physics courses. In addition, we now require our students to be able to program a computer. In what language does not matter so much. So if it's BASIC or Fortran, that's fine. Our computer science department offers 2 courses now. One is using Python, and the other is using C++. But programming in C or Java or HTML5, all these things, once you know these 2 languages, you can sort of teach yourself within a few days or maybe weeks. And all of these courses our students should take in the first 2 years. So what's the problem with this? The problem is that when the students come into physics, and even if they had mathematics, the calculus, they don't really understand the connections between the disciplines. So they see different disciplines as not connected at all. And the concepts that they have studied in mathematics, the limits, the derivatives, the solving of the differential equations, in their mind do not become connected to the applied cases in physics and engineering. Even though, if you recall, Newton and also Leibniz invented calculus to solve mechanics problems. Also, all the cases that we discuss in the physics curriculum, the introductory curriculum, you can write on the blackboard. They're analytically solvable, and the cases that you can't deal with analytically are usually just not even mentioned. There's really no numerical analysis that's taught in our introductory curriculum, and that numerical analysis, if it's taught, is not connected to the mathematics. And then computer skills that they learn in these classes also are seen as independent skills and are not to apply to real-world physics and engineering problems. And so these real-world complications are simply ignored in these introductory courses. And so a few years ago, a few of us from engineering and the sciences got together and tried to start from scratch. And we call this FYIE, First Year Integrated Engineering. And what we wanted to do was replace these independent courses in mathematics, physics, and computer science by one integrating block course. So these integrating courses then have the same credit value as the individual courses combined. Our introductory calculus course has 4 semester credits, our introductory physics course has 4 semester credits, and computer science has 3, and then the lab has 1. So that's a total of 12 credits. And for a full load in a semester, our students are expected to take 15 to 18 credits. So they can take 1 or maybe 2 more classes if they want to from another discipline to round out their curriculum. But the core block is worth 12 credits that they take 1 of these in the first semester and 1 of them in the second semester. We also wanted to go away from typical lecture format where the professor stands there for 50 minutes in front of the blackboard and teaches by just lecturing, and instead focus on problem-based learning courses. And one of the speakers later will talk about problem-based learning, so I just touched this in peripherally. This general instructional unit is then a problem, not an introductory lecture, and that problem needs to be solved by integrating different disciplines and concepts from these different disciplines. And I'll go through one of those in greater detail in a moment. So this is not lecture-centered, and instead we use flipped classroom technology, which basically relies on YouTube videos that we have put on the internet, and that the students are expected to have watched and probably also understood before the lecture begins. So these are typically of 5 to 10 minute duration. The reason for the 5 to 10 minute duration is that this is the typical attention span, the upper limit of the typical attention span of the typical 18 or 19-year-old. From personal experience, my son, who is 16, just took one of these computer science classes in a flipped classroom environment, and he liked this a lot more than any of the other classes that he had in high school. So for the younger generation, the so-called Generation X, this seems to be a much preferable format. We also are using scale-up style classrooms, and I'll show a picture or two later. So these classrooms is not organized like this lecture hall in seats that are all facing front, but in small groups around a table where about 6 or 7 or 8 chairs face the table and each other. And this environment encourages collaboration, and we want to teach the student to work in these collaborative work teams because in a real engineering environment later in their professional careers, they will have to work in these teams anyway. So why not start it with the university? We have a fairly large team, which is, alphabetically sorted. That's the only reason that I'm at the top. My initial partner was John Stickland from Computer Science and Engineering. So John and I hashed out the initial concepts, but as we got deeper and deeper into these discussions and I had more and more administrative duties, I sort of stepped back, and the main physics person became Stuart Tesmer, who took over from physics. And you can see there's a broad representation from engineering, from physics, even from Morten Hjort Jensen has a partial appointment at Michigan State and also at University of Oslo in Norway, and he has brought very valuable experience to this because they have also embarked on a similar path to us. We also have Jeff Grable from our writing department, because our students are supposed to deliver some of their projects that take the form of a physical review letter. And to do proper scientific writing actually also takes proper scientific writing training, and so that's why we included the arts and letters right away. Marianne Sildig is an external evaluator, is on our project team, and she's from Western Michigan University, which is about 100 kilometers away from Michigan State, and she is sort of supposed to give independent outside evaluation towards our progress. So let me just discuss one specific example, let's say trajectories. So the basic on which we solve trajectories in the physics and engineering curriculum is of course grounded in mathematics. And so in mathematics you would solve these differential equations. I have to wear my glasses to read my own writing here. And so Vx is the x component of the velocity vector and Vy is the y component. And this is just for constant acceleration g. And then, of course, dx by dt is the velocity in x direction and dy by t in y. So these four coupled differential equations, mathematicians like to solve, and it's an initial value problem of first-order differential equations in time. And, you know, a typical mathematician will do an existence proof and convergence, and all this is actually not so interesting, right? I mean, it's interesting for mathematicians, don't get me wrong, but for engineering students, they don't need to get into all this. All they need to really know is how to get to the solution. And of course, the solution, every physicist and engineer can write this down in their sleep. The x component of the velocity simply does not change. The y component of the velocity starts out at its initial value and then falls linearly with the slope g. The x component of the displacement is some initial value and then increases or, well, changes linearly with the initial x component of the velocity vector, and the y component has this parabolic shape. Okay, in mathematics you derive this, but in physics it receives meaning. And so in the physics curriculum we do basically the same derivation except for the existence proof and so on. And we show all kinds of cases. Well, first of all, you know, you want to define your coordinate system, so this is a three-dimensional, and then you bet you're two-dimensional, and everything happens in 2 dimensions, and you do videos like this one where you show the independence or lecture demonstrations live of x and y motion. You do parabolic trajectories like it's shown here. You do this shoot the monkey experiment where this projectile initially is aimed straight line at the monkey, and while the monkey falls, this projectile is still guaranteed to hit the monkey. Okay, to hit the monkey, and now. And so we discuss all these and the real physical implementations. We have extensions to this solution of the 4 differential equations that the physicists have. For example, we can derive the parabolic trajectory that the student, who is, by the way, my collaborator, Gary Westfall's son, shooting this free throw, and it actually worked on the first attempt, so we didn't do 20 or 30 tries. This was his first attempt. We can derive the range, how far a projectile goes, the maximum height. All this stuff is part of the physics curriculum. But, you know, we ignore stuff like air resistance, and clearly this ball rotates here, and we ignore that too. We can also have interactive simulations that are part of the curriculum. And so I wrote about 500 of these as part of my textbook development. And in this simulation, you can change the initial x component and y component of the velocity vector, and then hit the start button and see how the velocity components change in time. I said that earlier in the mathematics. It comes out that the x component doesn't change at all, and the y component decreases linearly in time. And this lets students visualize it by just playing with these parameters. And so, you know, you can change the x component and the y component, and you see the individual component and the sum vector, and then you start it and stop it wherever you want. At the top of the trajectory, and you can see the horizontal component stays constant all the time. And you trace out the parabolic trajectory, right? So that's just one example. We have an ebook that integrates all of these. So if you had clicked on this button here, that's exactly what you get. These look like they can run on an iPad, and indeed they can. So maybe 15 years ago, I had written many of these applications in Java, and unfortunately Apple decided that they would not support Java, so my Java work was kind of useless, and so I had to learn HTML5. So all this stuff, all these 500 or 600 applications that I wrote initially in Java, I had to then write in HTML5, but better. There's also concept checks, which are the same kind of idea that Eric Mazur just got this Minerva Prize that Helio Diaz mentioned for. They can be used for peer instruction and for self-tests. They are simple conceptual questions with maybe 4 or 5 different possible answers. We use them typically for clickers and peer instruction in class, but you can also do them as self-tests like this. We are presently working also on a Portuguese version of this ebook. The hard copies you can buy outside, or if you talk to Helio Diaz, maybe he can make you a good price. But there will be an ebook available also, and we just started work on this. What we ask the students to also do, of course, is solve problems. This is not exactly the kind of problem-based learning we want to get to, because these are basically introductory problems that you can solve on a piece of paper, you know. So here it's for some competition, a group of students builds a trebuchet, which is, you know, one of these guns that can shoot a projectile and fire a tennis ball from some height. And so what horizontal distance will the tennis ball cover before it hits the ground? So typically we ask the students to solve this on a piece of paper like this. This is a really good student. He really understands everything, because it was just me writing this down, of course, not a student. And so, you know, you start with a drawing and put all the parameters in, then you solve, and finally you figure out a number. And this is actually very involved to grade. And so we ask the students to work with pencil and paper, but then they have to hand it to the other students, some other student in the class, that anonymously will grade it for them. And this is basically for all of them expected to be completed, and everybody gets full credit, because if you don't give everybody full credit, then all kinds of cheating will take place. But we just need them to take this serious, and they can hand their work back to their colleagues and then improve on their own work in the second step. We can also use the computer to do the grading for us. So while we want to have maybe a few cases, 2 or 3 per week, that they work on with pencil and paper, the overwhelming number of problems that they're expected to solve, they're expected to do on the computer. So we have this computer grading system. The first version of this was called Lon Kappa, and now we switched to a new company that has taken this Lon Kappa system over and improved it. It's called CourseWeaver. And so this is exactly the same problem with different numbers that I just said. Every student will see different numbers, but basically the same problem, which prevents people just telling each other the answer. And there is an input field that the students can type in a numerical answer, and then a submit button. So let's say they typed in 23, then, you know, this is a distance, so it requires a number plus a unit, and so the computer answers, hey, you need to enter a unit, and we don't even count this as a bad try. You just forgot the unit. Please think about this. So then maybe you enter 230 meters, and that's incorrect, and so now your try has increased. The professor can specify how many tries you allow. I typically allow 99, because that's a really large number, and no student will ever go that far, so I don't care how often they try. And so eventually they think enough, and they put the right number in, which was 23.1 meter here, and then they get the evaluation that they are correct, and this is entered into a spreadsheet and kept for their grade in the homework portion. And the exams are actually done in the very same way. We can also let the students take exam on these computers, or print the exams out and let them work by hand. So this is, as I said, all done by some system called CourseWeaver now. This also, later this year, will be available in Brazil through this partnership with the Science Club. And the students won't even have to read English, so there's a Portuguese version that's in the working. We also have put a new teaching innovation in which we call multi-version exercises. So this is actually that problem that I just solved by hand from the textbook, but then you see there are 3 more versions that read almost exactly the same. But if you look carefully, it's the same problem with the same numbers here. So here's the horizontal distance is asked. Here's the x component of the velocity. Here's the y component of the velocity, and here's the speed. So it's basically the same problem, but a different answer. If a student understands how to solve this problem, then they can rearrange the terms to find a different answer. Now, why do we do this? Well, our students always complain that the homework problems and what they heard in the lecture was not connected to what they then saw in the exams. This goes around this problem. Now, I could also just say, hey, I solved this in the lecture, and then I give it to you in the homework again, and then I give it to you in the exam again. But if it's always the same problem, the students find this out really, really quickly, and they just memorize the answer. In these multi-version ones, they really have to understand, if I solve this in the lecture, and I give them this in the homework, and then this on the final exam, they really have to understand it. They can't just memorize the answer. But it's very important that the students see the connection between what they do in lecture, in the homework, and the exam. And so there are on the order of 100 of those multi-version blocks that we include in the materials. But this is still how the conventional physics course would approach, and then stop there. But for example, if you hit a baseball or kick a soccer ball, football here, right? Or hit a golf ball, then you see that the trajectory that you calculate in the normal physics approach is not at all the trajectory that you get. And here are 2 examples. One initial velocity of 90 miles per hour, another initial velocity of 110 miles per hour, and then you see the distance that you calculate from conventional trajectory calculations. But here's the distance that the real projectile will fly, a real baseball in this case. Now, this includes air resistance, it includes the rotation of the ball, and you have to solve this numerically. And so at the same time that we introduce the trajectory concepts in mathematics, where we solve the differential equations, and then in physics, where we do all the extensions that we need for the physical understanding, in the same week, we also teach programming concepts that are related to solving this trajectory, to solving the first order differential equation in time numerically. We are agnostic on what language the instructors are supposed to use, and actually some in our team are really fond of Python, some are fond of MATLAB. I'm kind of partial to HTML5 and Mathematica, but if you want to use any of these others, that's great too. But the students will have the same programming language all through the semester, so they don't have to switch between languages. So these programming tasks are assigned, and then proper numerical analysis techniques taught. So for example, you could do an Euler method, but for this simple system it actually will work out, but in general it's rather useless, and so we teach them the 4th order Runge-Kutta in this case, which is what professionals use to solve these first order differential equations in time. So there are also skills beyond this that students need to learn. They need to connect what they have done theoretically and on the computer to real world situations. So we put heavy emphasis on analyzing video footage. And students, and also this instructor, for example, are really interested in sports. And so we can use sports videos to accomplish this. And in order not to contaminate what we do in our course, I just used a different example for you in the next couple of slides, and I'll do this. But this is not an example that we would use in class because, Helio will put this on the web, and then it's easy for the students to copy what I just did. So we compare the theoretical and computational findings to real experimental situations, and so there's an integrated laboratory experience that can be both laboratory experiments that you touch or laboratory experiments that you conduct on the computer. You also solve real-world engineering tasks by designing structures and devices, designing performance tests for your designs, and then conducting these performance evaluations, just what an engineer needs to do. And so I'll just give you one example for this video analysis. This is just from baseball, where one of my favorite players, Miguel Cabrera from my hometown team, the Detroit Tigers, hits this baseball, and this is called a home run. It, it leaves the stadium. And what's actually special about this particular game is that he did the same thing 4 times in a row, which has only been accomplished 11 times in history by any player. So that's why I picked this video clip. But you can analyze this video clip frame by frame. And so I start this here. This was part of what you just have seen, right? Where the ball is here and I mark it with the yellow circle, and Miguel Cabrera has already started his swing and the ball is still, 4 meters away from him. You see his bat is kind of blurry here. And then as I step through the frames, I mark the ball with these yellow circles in each video frame. And so here the bat meets the ball. Unfortunately, I picked this video clip and the ball actually travels pretty much along this line in the air, so it's hard to discern where the ball is. You just have to believe me that I actually did this exercise correctly. You can sort of see it blurry there. And then, so you have all the positions of the ball in time for each frame, and you know that each frame is 1/30th of a second separated. And so you can overlay, in this case, I was concerned about initial and final momentum and the momentum transfer or impulse. So this is the initial momentum, where I say, okay, it's proportional to 5 of these time steps. And here's the final momentum. And then the difference, PF minus PI, that's the impulse. Right? So it's, what we're also working on, but what we haven't perfected, is to integrate gaming ideas into our lecture so that the students can interactively play with little scenarios like this. So this is a problem where a goose will fly over a car and drop some excrement and hit the windshield, and so that's going to be your task. And for that you really have to understand trajectories. So the goose comes in with some, when you hit the start button, with some random velocity, and so there goose missed. And then here, very close, but not quite the windshield. And you try again, and then, well, you hit the windshield. So, while this is just sort of an initial attempt, there's great potential in this. And in particular, as the students become more proficient in programming, we can let them improve these simulations to make better and better gaming situations out of them. This is all programmed in HTML5, which is a very convenient language because it also runs on an iPad or iPhone. And you can make these as complicated as you want. So for the physical space, our physical spaces are not quite done yet, so I just used one of the original scale-up classrooms from, I think this is North Carolina State. And you can see these collaborative spaces with 8 chairs around a table. And then there's a ceiling-mounted projector where students can have access to it and work together on the same screen. We also make sure that the students are housed together. Now you can discuss, is this really a good idea? But what we want for the first-year students and maybe the second-year students is that they form an integrated cohort and make friends and establish social connections with students that have the same goals in their careers. And so we actually house them all together on dedicated floors in this engineering dorm. And we call this core experience, cornerstone and residential experience, where our sort of slogan is building the whole engineer. Through residential experiences, through academic experiences, and through common social activities. And with social activities, I really mean social not as in social media, Twitter or Facebook or whatever, but maybe playing games together, you know, going out on the football field. So here's my summary. What we're trying to establish is this first year integrated engineering curriculum, which is a tightly integrated interdisciplinary curriculum consisting of mathematics, physics, and computer science. This is already pretty much established. What we want to do in the next attempt is maybe instead of having physics, also a chemistry track and a biology track, because there's also chemical engineers and bioengineers and so on. We are using problem-based learning, flipped classroom technology, and we want to create a new student experience where they are working and living in collaborative teams, and where we form real cohorts that establish friendships that hopefully last not just through their college experience but through their life. I can't make this promise yet that this will really happen, because obviously they haven't graduated yet, but as they move through the ranks, we will do a follow-up study to investigate this. And I thank you for your attention.